All right, so hopefully everyone can see my slides remotely and hear me and see me. Let me know if anything's off there, but we should be good to go. All right, so I'm Sean Barker. I'm an associate professor of computer science at Bowdoin College in the US. And today I'm going to be talking about our work on identifying impactful devices on disaggregation performance. This is joint work with two of my undergraduate students, Anna Lettner and Andy Stoneman at Bowdoin. All right, so I'd like to start by sort of telling the classic story of NILM, which I'm sure all of us have told many times. Right? My subject here is going to be Alice, who let's say is a homeowner interested in her energy consumption. Right? So the story goes something like this. Right? Alice says, I have this smart meter giving me this information about my aggregate energy consumption. I wish I understood more about where all of my energy use is going. Right? And so you enter and you say you've come to the right place. Right? I've got this great disaggregation algorithm, right, that's going to analyze all of your aggregate energy consumption, right, and tell you exactly how you're using all of your energy. So your energy is being consumed by your toaster, your television, your washing machine in these proportions and so forth. Right? And Alice says, okay, that's fantastic. Can I invest in your startup? Right? Now, that's sort of, that's a nice story, and Alice is happy. Right? Alice also has a next door neighbor. So this is Bob here. Right? Now, Bob also has a house, but Bob's house is a little bit different than Alice's. So Bob likes electronics and appliance stores, right? And this is Bob's house, right? And so, Alice says, I have this great NILM algorithm, you should try it out. Bob goes and tries it, and unfortunately, things don't work quite so well for Bob, right? Because, unfortunately, when we have a huge number of devices, right, it's hard to model that many devices. It's also hard to get sort of a complete energy breakdown, right, of all of these various devices. Right? This was something that came up in our keynote today, right? So, unfortunately, right, for all of us, people in general and buildings are going to be more like Bob's house used most of the time as opposed to Alice's. There's typically going to be more than just a few devices that we might want to try to disaggregate. So what do we do about this as NILM researchers? Well, one option is to sort of just pretend that everyone is like Alice, right? We're only going to run tests on sort of small environments with only a few devices, and that might be convenient for running experiments, but not terribly realistic, right? A different alternative is, well, maybe we're not going to worry about trying to provide a complete breakdown of energy consumption. Maybe we're just going to choose a few of Bob's particular devices that we're interested in, try to disaggregate those without worrying about the rest. Right? That might be much more doable, right? But there's still going to be some challenges owing to all of the other things that are part of Bob's aggregate consumption. So really the question here is, how do we get this to scale well, where even in an environment like Bob's, we can still do reasonably accurate disaggregation, right? So that this is working well, both for people like Alice and people like Bob here. So let's consider sort of what are some of the challenges, or how do we sort of characterize the challenges here in scaling NILM? And the sort of, your first impression might be to simply say, well, the problem here is there are too many devices. Now, I'll argue that that is actually sort of perhaps overly pessimistic, because one, there's not really anything we can do about that. We can't just tell people, be more like Alice, have 3 devices in your house and the problem will be solved. But there are some other possibilities that I think we should consider. So one example, perhaps the problem is not so much that there are too many devices, but that there are too many devices that are similar to each other. So maybe the issue is not that Bob has 50 appliances, it's that Bob has 3 refrigerators that have very similar usage patterns, and that makes things difficult. Now, a sort of slightly more general way to describe this is we could say, well, maybe the issue is simply that there are certain devices that make disaggregation hard, right? So maybe I have a whole bunch of lights that have sort of very straightforward consumption. Those are not going to cause a problem most likely. But then I've got other kinds of devices that are much more complex, right? Lots of oscillating patterns, right? Different shapes that we can see. Maybe those are what is really causing problems here. So in this work, we're really kind of interested in this third possibility, that how much of the difficulty from scaling NILM to these complex environments comes from specific devices that might be making things difficult. Now, of course, if we're considering that question, the natural follow-up question is, well, okay, if this is the case, which devices are the most impactful and how can we identify what they are? So this is sort of the key question that we're investigating in this work. So let's think about how we can approach this problem. Right, so to start, what we're going to do is we're going to take all of the devices in our home or building, and we're going to divide them into two groups. So first, we're going to consider a couple of devices that we're actually interested in disaggregating. So these are going to be what we call our foreground devices. Right? These don't need to be every device in the house, right? But these are going to be what we're actively trying to disaggregate. Everything else in the house, we're going to call our background devices, and these are going to be devices that we are not trying to disaggregate. So they are present in our aggregate consumption, but we're not actually trying to extract them using our disaggregation algorithm. So the basic thing we're going to do with this distinction is we're going to fix our set of foreground devices while we vary the set of background devices. And the idea of doing so is that we are going to be able to see how the background devices are affecting the disaggregation performance of a fixed set of foreground devices. So that's going to be the basic idea here. We're going to be measuring the performance of disaggregation on these fixed foreground devices. Now, let's say, for example, as a starting point, that we wanted to decide which one of the background devices was most significant, having the largest impact on disaggregation performance. Well, here's a simple way we can do that. First, pick some background device sort of arbitrarily and remove it. Once we've done that, we're going to retest, we're going to re-disaggregate the foreground devices and measure the improvement from the baseline, right? The baseline being where all of those devices were included. After we've done that, we're going to put the removed device back and retest on some other device. So pick some other background device, remove it, run disaggregation, and so on and so forth, essentially running through all of our background devices. Right? And once we've done that, we should be able to determine which one of these had the greatest effect on the disaggregation performance of those foreground devices. Now, one important question here is, well, how are we actually measuring what this improvement is? Like, how do we actually decide how much we improved? So here's the way we're thinking about that here. Right? The way we're basically scoring each one of these disaggregation trials is we're going to pick some metric. Pick your favorite NILM metric, right? Another thing that came up in our keynote, right? F1 measure, right? MAE, some other metric. Pick your favorite metric. And when in each one of these trials, we're going to consider that metric over the foreground devices and just sum up the improvements. So, sum up the F1 improvement, sum up the MAE improvement for whatever metric you want. And that effectively is going to give you a numeric score for the trial. And using that score, you can decide which one of your background devices was most significant. So that's a nice sort of straightforward approach. But what would be more interesting than sort of just deciding what the single most significant background device is here is really we would like to be able to pick a set of top devices, like consider finding the top K devices. And this is going to be a little bit more challenging, right? Primarily due to the fact that our devices are not going to be independent. So if I, for example, remove one background device, that can potentially have effects on how significant the other devices are. Right? It might be the case that the removal of one device renders some other device either more or less significant in the complete disaggregation problem. Now, the optimal approach to this is to just try every combination. So if we've got n devices and we want to find the top k, we can just choose every possible set of k devices, run n choose k trials. That will give us the best set. Right? But of course, here we have combinatorial explosion. That's not going to be so tractable if we have a larger number of devices. So instead of doing that, what we're going to propose is basically trying to greedily approximate what we would get from the optimal approach. And the way we're going to do that is by running multiple of those single device rounds that I just talked about. So we can run one round to find the most significant background device, then actually remove that, run a second round to estimate the second most significant background device, and so on and so on. And with that kind of approach, we're going to be able to find n times files, which of course is going to be much more tractable here. So that's the basic approach we're using. Let's talk about how we actually ran experiments here. So we ran all of our experiments using NILM TK, both a mix of some of the sort of classic disaggregation algorithms like edge detection, as well as some of the more cutting edge algorithms, mostly based on neural nets. The data we considered here, we used enough from Dataport. So what we did was we selected a range of devices, 35 in total, across a broad range of different types of devices, and also selected to make sure that all of those devices had a reasonable amount of activity. And then we considered 2 months of data here. So we used 1 month for training, 1 month for testing. We trained all of our neural nets for 50 epochs. Our data resolution was 10 seconds. Pretty much most of the other parameters involved were sort of left at their default values. And for actually scoring each of our trials, we considered 2 different metrics, right? F1 score and MAE, mean absolute error. So let's talk about the device configurations in each one of our trials. So again, each one of our experiments is essentially set up with a fixed set of foreground devices and then a variable number of background devices. So we chose 4 specific devices to use as our foreground devices: our refrigerator, dishwasher, microwave, and washing machine. These are all pretty popular devices in disaggregation work. And then our foreground devices are going to be up to the 31 other devices in our total set of 35 devices. Now, there are 2 baseline configurations that we should pay particular attention to. Right? One is the configuration where there are no background devices. We're going to call this BG0. Essentially, that's the Alice situation, where there are only a few devices and we're trying to disaggregate everything. The opposite extreme is where we have all of the background devices. We're going to call that BG31. All 31 background devices are present. And again, we're still trying to disaggregate the same set of 4 foreground devices, but now there's a lot more activity happening in the aggregate trace. So let's talk about how this actually works. So first, what we looked at is what happens when we start with the BG0 configuration and gradually add background devices up to the BG31 configuration. And we looked at what happens to disaggregation performance on the foreground devices as we do that. So let's look at some graphs that show that. So here are 2 graphs. Right? On the left-hand side, we have F1 score. On the right-hand side, we have MAE. So what we're seeing here, on the y-axis we have the relevant metric, right, F1 on the left, MAE on the right. Along the x-axis we have the number of background devices present. So again, the left side of both of these graphs is the BG0 configuration, the far right side is the BG31 configuration, and in the middle is some subset of those 31 background devices. We picked an arbitrary order here. The order was not chosen deliberately. So essentially what we see here, and each one of the lines on each one of these graphs is one of the disaggregation algorithms that we tried. These are all standard algorithms in NILM TK. We've got edge detection, denoising autoencoders, sequence to sequence, sequence to point, and recurrent neural networks. So again, all sort of standard algorithms built into NILM TK. Now, as we would expect, probably unsurprisingly, what we see here in general is performance gradually degrades as the complexity of the operating environment increases. Right? So F1 scores are generally trending downwards, right? MAE scores are generally trending upwards. And so that's, again, pretty much what we would expect to see here. Now, we're not attempting to rank anything here, right? But what's actually more interesting, so these graphs here are showing the overall performance. So these are all of our foreground devices essentially averaged. But we can see some interesting things when we look at specific foreground devices individually. So let's take a look at what that looks like. So here is the same 2 graphs, right, but showing performance specifically on the refrigerator rather than all 4 devices overall. Now, what we see here is that the refrigerator is a pretty easy device to disaggregate. Right? We see, for example, the F1 scores are close to 1 for all of these algorithms. And although there is some degrading performance, right, even with all of the background devices, our F1 scores are still around 0.7, 0.8, thereabouts. So this is an example of a device that is pretty easy to disaggregate, even with many devices, which I would posit is one of the reasons refrigerators tend to be so popular, right, in disaggregation work. But this is not true of all devices. So as another example, let's consider the microwave. So when we look at the microwave, we see something that looks very different. Right? So here, even with very few, even no background devices, right, performance on the microwave is much, much worse. Now, as we add devices, performance gets sort of somewhat worse, but actually not significantly, because we weren't doing that well to begin with. So on a device like this, what we're seeing is that it's sort of hard to disaggregate very well, even when there aren't very many devices present. Other devices show other characteristics. So for example, here's what the dishwasher looks like. Right? Now, what we see here is that performance with a few devices is quite good. Right? But as we add background devices, as the complexity of the environment increases, performance drops off very significantly. So this is different than what we saw in, for example, the case of the refrigerator. So essentially what we're seeing here is this is an example of a device that is very sensitive to the complexity of the environment. Right? As we're adding more and more devices, it becomes very hard to accurately disaggregate what previously we could handle very well. And finally, just for completeness' sake, let's consider the fourth foreground device, which was the washing machine. Right? Here we see something that looks kind of odd in that there are sort of very rapid oscillations between what appears to be okay performance and not so okay performance. And again, you can mostly see that in the F1 scores here. Right? And what we're seeing essentially here is that this particular device is very sensitive to what the operating environment is like, so performance is kind of unstable. Right? But the key point here overall, right, takeaway message here is that these different devices can react very differently to the exact same changes in the operating environment, right? Because these set of devices we're adding is the same set, the same sequence in all of these cases, and we see very different behaviors. So next, let's consider the sort of initial question that I mentioned was sort of characterizing the most impactful devices. So as a case study here, we considered, suppose we wanted to approximate what the 5 most significant devices are using that greedy algorithm that I described earlier. So in order to actually produce a ranking of the top 5, there are a few parameters we need to set. Right? One is the particular NILM algorithm we're using in each one of our trials. So we considered 2 possibilities. One was edge detection, kind of as a simple baseline, and then the other was sequence to point, which in most of our experiments was either the best or one of the best performing algorithms. Second parameter is we need to decide the number of greedy rounds. So 5 rounds would be exactly the greedy algorithm as I described it previously. You run through all of your background device, pick one device to remove, then do a second round to pick the second background device, so on and so forth. As an alternative, you could consider just running 1 round to get your ranking of background devices and picking the top 5 all at once. So that's going to be what 1 round would mean. Right? You're likely to get somewhat worse performance from doing that, but it's easier to compute. Finally, as a third parameter, we have to decide what scoring metric are we going to be using to compare all the trials. And again, we consider either F1 or MAE. So you can take any configuration of these parameters here, essentially plug it into the greedy algorithm as I described, and it will spit out what the top 5 devices are. So there are a whole bunch of different configurations, basically all combinations of these 3 parameters. Right? This table, which is reproduced from the paper, I'm sure it's hard to read, shows what those top 5 devices are. Right? Now, there's obviously a lot of overlap across these various device rankings, but to sort of summarize at a high level what most of these devices are, they tend to be devices that are frequently operating, often cyclic, and often high power devices. So things like air conditioners and freezers, right, are very well represented in these top 5 devices. We also considered one additional configuration, which was sort of manual selection, where we as a human expert are sort of picking 5 devices to withhold sort of as a baseline here. And those would be looking at things like picking devices that are similar device types to what is being disaggregated in the foreground set. Now, there's still a significant amount of variation across what the top 5 devices are that are estimated using each one of these configurations. So to decide which ranking is best, we tested them all. So what we did here was for each one of those rankings, which put out 5 devices that were estimated to be the most significant, we removed those 5 devices, ran the disaggregation using sequence to point in all of these cases, right, and then computed the MAE and F1 scores. So this is a graph that shows that. So along the x-axis, we have each one of those configurations. Along the y-axis, we have the resulting MAE in red and the F1 scores in blue across all 4 foreground devices. And so the few things that we should pay particular attention to. Right? First, on the left, we have the 2 baselines. So notice BG0, that's the easiest case. So we have the lowest MAE and the highest F1 score. BG31, the other baseline, is the hardest case. So there we have the highest MAE and the lowest F1 score. All of the other configurations are 26 background devices, right? And the 5 that are not included are the top 5 selected by that configuration. So essentially what we want out of those configurations is we are interested in configurations that get us as close as possible to BG0, because it basically means those 5 devices that are missing are responsible for most of the added complexity from all of these extra devices. So the best ranking we see here is this ranking ED5M. So this was the ranking produced, interestingly, using edge detection, right, as our trial algorithm, right, 5 rounds looking at the MAE scores. So when we consider this particular ranking, right, and removing those 5 chosen devices, and we compare to the baseline BG31, we're effectively recovering about 40% of the F1 loss between those 2 baselines, and we're recovering close to half of the MAE loss. And again, the reason this is significant is that we're only removing about 1/6 of the devices in question here, right? And in doing so, we appear to be eliminating about half the complexity, right, of the problem. So this is again pointing to the very outsized influence, right, of these particular devices here. We can also look at the behavior of each one of the individual foreground devices as we remove these top devices. So this graph is showing as we remove up to those 5 devices chosen by that best configuration we were just looking at, right, what the F1 and MAE scores look like for each of the foreground devices. And as you would expect, F1 tends to trend upwards, MAE tends to trend downwards. But one thing that's interesting to note here is that we see the largest improvements, particularly in the F1 scores, from those devices that I mentioned are most sensitive to background activity, right? Namely the washing machine and the dishwasher see very significant increases, right, because they are so sensitive to those background devices. So to quickly summarize, right, obviously disaggregation at scale is hard, particularly when we're talking about trying to disaggregate all the devices, right? But even if we're only trying to disaggregate a few. Right, what we've looked at in this work, right, is the fact that a small number of devices may have an outsized impact on disaggregation complexity, right, which is a reason that we should consider trying to focus on these. Right? So as a simple example, if there's one device that is particularly problematic, maybe it makes sense to do something like put a device level meter onto that device to try to simplify the rest of the disaggregation problem. Right? So we really should be interested in devices that make disaggregation hard, even if those are not the devices that we are actually trying to disaggregate. And we've taken some initial steps in this direction, but as sort of ongoing and future work, right, what we're interested in is trying to characterize what these impactful devices are, right, and be able to rapidly identify them. Because even here, we still had to run a lot of trials to determine what these impactful devices are. It would be better if we had, say, an easily computable heuristic to be able to identify or predict what these important devices are. And I will stop there, and I'd be happy to take any questions.